Thank you, Professor.
You're welcome. All right, so here we go. So we're going to look at a few properties of definite integrals. So this is the first one. There's actually three, I think, in this section. I copied them down. Yeah. So here we go. So this is what we're saying. If you have a definite integral here from a lower value to an upper value, a to c. So we're going from a to c. You can find the definite integral by split it into two parts. So and adding them together. So if you were to take a definite integral from a to b, which is what they're saying here, and then take the indefinite integral from b to c and add them together, you get the same result as taking it from a to c. Make sense to everyone? Now, why would I want you to do that? That's a question, right? We're going to look at the first question in 4.4. And if Samira thought the previous section was a lot of work, she's in for a surprise here. So this is number 1 in 4.4. Now, the reason why they generally do something like this, or emphasize this rule, is that because not every function, like we have here, is continuous and it's a single function. Sometime in math, we have graphs that part of the function looks like this, and then another part looks like this, where there's a curve, there's a line, or it can be two separate curves, right? So you cannot integrate directly from A to C on a function like this because there's two different functions. So you have to split it up in two parts and do from A to B and then from B to C to get the total area. Only because the functions are different. That makes up the whole thing. You might recall this from college algebra. These are called piecewise functions. So they're made up of, multiple parts of different functions. They could be 2 parts, 3 parts, 4 parts. And number 1 is such an example of a function like this. If you were to sketch this function, let's go again to the sketching. Let's start with the x squared plus 1. This is a parabola that intersects the y-axis at 1. So we know that this looks like this. And then we have a line. This is y is equal to 2x. If we're to sketch that line, let's use a different color here. Kind of looks like this. And to sketch a line, all I'm doing is plugging in points. So when x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to 2. So here's my curve and line combined. Now they want the area from 1 to 3, negative 1 to 3. Now from negative 1 to 3, you can see, it's two different curves, obviously, right? Now for the line, they're interested in the section that's greater than 1. So for the line, all we're interested in is this section. We do not want a section, it's probably, there you go. So we do not want that piece of the line, because for the line, they're only interested in the piece that's greater than 1. And for the curve, they're interested in a piece that's less than 1. Move this rule down a bit. So here we go. So we're taking the integral then. So the area we know is going to be the integral from -1 to 1. So we have to add these together, which is the first part. So we're going to take the integral from here to here. That's a definite integral. And this is also a different function. This is x squared plus 1. And we're going to add that to the integral from 1 to 3 of 2x. Does everyone understand what I'm doing? Or you get lost? I'm just splitting it into 2 parts because of the 2 curves.
Can you scroll down just a little?
Down,
Only because, yeah.
like there?
Yeah. Okay.
But does that make sense what I was saying, Lewis?
Splitting it up? Like splitting
Yeah.
it? Yeah, I see what you're doing.
And I'm just splitting up because it's 2 different equations. If it was 1 equation for the whole graph, then we don't have to split up. Like all the problems before was just 1 equation for the whole graph. But here they're giving us 2 equations. This is why we're splitting it up.
Okay. Okay.
And once we split it up, you know, that's the difficult part. I mean, everything else is just going back to what we just did. So we're going to find the antiderivative of this, which is x to the third over 3 plus x, which we're going to evaluate from -1 to 1. Let's erase this a little lower so they can both fall in the same line. So this becomes x to the third over 3 plus x. I'm going from -1 to 1 plus. Now we're going to take the antiderivative of this piece, which is a 2x, which becomes 2x squared over 2. And we're going to do that from 1 to 3. Now the 2's here will cancel. So this is all plugging in at this stage. 1 to the third over 3 plus 1 minus -1 to the third over 3 plus -1. So all of this is for the first piece here. We're plugging in 1 and -1. Now we're going to do the same thing with the x squared. So we're going to plug it. And this becomes 3 squared minus 1 squared. And all of this was the second piece here. So more arithmetic than anything else. So it's 1/3 plus 1 minus, that's negative 1/3 minus 1 plus 9 minus 1.
Professor,
Yes,
can you explain real quick how you got 3 squared?
3 squared. Okay. So just above that, we have the x squared because we canceled out the 2's. You see that?
Yeah, I see that.
All right, so now all we're doing is substituting. So we're plugging in the 3 first,
Oh,
and then we're going to plug in the 1.
okay. Oh, wow. All right. I see. Okay.
And on this one, we're plugging in the 1. And
Yeah, I see that part.
all right.
All
Yeah,
right.
so yeah, we took the, you're just plugging in. Now it's just a matter of arithmetic.
Okay. Thank you.
Just, so it's 1/3 plus 1. This becomes plus 1/3 again, plus 1, plus 9 minus 1. All right, this one will cancel this one. So that's 10 2/3. If you wanted an exact answer, it's what answer, if I have an answer for that. And I do not. Assuming we made no arithmetic error, you know, that would be your answer for that problem. And the good news is, you know, there's just one such problem in the homework. So I had to cover it.